Testing 5, 6. Thank you, Maya. Appreciate that. It's great to be here. I think it's really exciting to get a group of people interested in both neuroscience and AI together to talk about their favorite things. So as Maya mentioned, one of my favorite things is this Spaun model that came out of my lab quite a long time ago. So it was 2012 was when the first paper on Spaun came out. And we're now a couple of generations past that original work. And today I'm going to talk to you about what is really a work in progress. So Spaun 3 has not been published, and we will not really be publishing it for a little while, but I think it's fun to show people what we're up to. So in order to connect to today's theme, though, I also want to talk about how that model, which is really a brain model, is related to techniques and methods in AI. And I think these connections have become sort of tighter over the years in my lab, actually, as opposed to anything else. So I think we all know that current AI is pretty impressive. It can do lots of things that nobody would have expected 3 years ago for it to be able to do, but it also has limitations that we don't see in biological intelligence. And so it seems like that's a good opportunity, potentially, to learn about how to overcome those limitations, or at least understand them better. Some examples of this are that you do not have sample efficient learning a lot of the time in AI models, the really big ones in particular. So yeah, having the right kinds of inductive biases, as Zach has kind of turned me on to in the last year or so, is really critical in order to have the kinds of behaviors that we see in biological intelligence. And you also find in LLMs in particular a lot of imprecise reasoning, right? So if you try to get it to do simple math, what we would consider simple math, I give you 2 3-digit numbers to multiply together, you can sit down and you can do that, and you can do it accurately, and typically you're following some kind of algorithm in your cognitive sort of reasoning, and that gets you to the right answer. These models don't seem to be able to do that kind of thing, right? You can do lots of work to try to get them to overcome that, but they're just basically generally bad at having some reliable reasoning technique that they can apply in the right sort of circumstances. So on the other side, when we're looking at models of biological cognition, one reason we want to do that is because it can help us potentially uncover principles that have been missed in this more sort of functional approach that is typical of AI. So those principles might be things like, how do we induce the right kind of inductive bias to get more sample efficient learning? How can we incorporate the right kinds of representations and methods inside these large language models in order to improve the precision of the reasoning? So today we're going to see 2 examples of that, of these things. And I've got little stars in case I forget to mention that I'm giving you one of the examples. I've got stars beside those. Because really what I'm doing in this talk today is telling you about Spaun 3, right? And so it's not, the intent of Spaun 3 isn't really to sort of overcome these limitations of AI, but I think it is kind of lets us move in that direction in the ways that I just described. So just to give you a sense of sort of how my lab works and where these large brain models fit into our work, essentially what's happened since the publication of Spaun 1 is that every 6 years or so, we put together all of the new models and methods and techniques that different individual students or postdocs have been working on in the lab. So a big integrated model is kind of not one person's job. It's more like, a student will pick a particular area they're interested in. They might be interested in navigation, or they might be interested in motor control or vision or something, learning, what have you. And they'll really work on a specific sort of solution to that problem, or trying to get more insights in that particular area. And then after a lot of people have done that over 6 years or so, we were like, okay, let's take everything that people have done and see how much of that we can put together. The idea being that the whole is greater than the sum of its parts, right? You can start asking questions, getting insights that you can't get when you just look at individual models. So as I mentioned, Spaun 1 came out in 2012. Spaun 2 came out in 2018. And what we've been doing since then, I've been focusing on a couple of core theoretical issues, which I think you can generally think of as understanding how to represent continuity in a way that brains seem to. And this makes us think about things like representing continuous space. So how do you have maps where you can have features located at any point throughout a map? So a lot of modeling, we worry about having sort of structures which are sort of like strict orderings or tree-like relations and so on. But maps is something that brains are particularly good at. And we've always been working on this. If people have heard about place cells, grid cells, and so on in the hippocampus, that you know that those kinds of representations are in the brain. but having a really nice sort of theoretical understanding of where they might come from, I think has been missing. Same thing in time. So time cells also in the hippocampus, discovered in like 2014, and people started thinking about, representations over continuous time, like over some window or some period, being something that brains naturally generate and they're very good at working with. The sort of intuitive way of understanding this as being new is that if you're familiar with working memory literature, the typical way that you test working memory is you give people a list of items, and then you get them to repeat that list back. And you can basically say, repeat them back in the order I gave them to you, or just repeat them back in whatever order you want to, right? So that's free recall and serial recall. So what have you imposed on people in giving them this as a working memory task? Basically that the order matters, and this is all you would test, right? You'd say like, oh, here's the order. This is how many people get right when it's halfway through the list, or if it's at the beginning of the list and the end of the list. So everything is very discretized, right? You have basically slots, you have things that the order is all that matters. And if people do the task, then you think, oh, okay, now I've got an understanding of working memory. But if you think about your own working memory, it's temporal, right? So you do care about the order things happen in, but you also know how far apart they were in time, right? So if you think about, you had lunch, you spent a certain amount of time in, so you know the order, right? You lined up, you picked up your stuff, you sat down, you ate, you had a conversation. So that's the order, but each of those took a certain length of time. And if you recollect that, you can give very accurate descriptions of how long those things took, right? And so in the psychological literature, there's kind of a subfield where they look at timing and they distinguish between retrospective and prospective timing. And you can show that people are, quite good at estimating intervals of time and all these sorts of things, but most of our models are not good at that, right? The models have generally been constructed to be able to will definitely capture that things are remembered, but then maybe capture the order in which they're remembered, but generally not capture the information about how long did that event take compared to the other events, or how long apart were those different events. So, so I think, intuitively brains are very adept at representing information over continuous time and being able to report on it, but a lot of our models haven't been. So also important. So time and space, and then uncertainty, which is actually the one I'm going to talk the least about today. But if you're essentially representing things over a continuous space, then you can think of a probability density function as a kind of continuous representation of uncertainty. You also have discrete representations of uncertainty. And I'll just leave it as a talk to me after, that the same representations we can use over space and time can be used for doing uncertainty representation. So today, what I'm going to do is briefly talk about some of the general techniques that we use to address these issues, but more generally build large-scale brain models. And then I'm going to tell you about some of the early versions of Spaun, just to give you a sense of like where we're starting from. Then I'll give you an update on a current work in progress for Spaun 3. And I'll, during that, give you an example of integrating Spaun-like methods into an LLM to show how we can improve the representation or the performance of the LLM of particular types of tasks. All right, and I'm also happy for people to, if they have a clarifying question, just to interrupt so I can address it right away. But anything more substantial, please save. Okay, so back many years ago, in like 2003, Charlie Anderson and I published this book called Neural Engineering. And this forms the set of techniques that even to this day, we generally use in building these large-scale brain models. We think of this as a kind of neural compiler. So it lets you specify some high-level function, right? So typically, we like people to specify those in terms of a dynamical system. So you write down a differential equation of some kind. So if you're doing working memory, you could write down the differential equation dx dt equals 0, right? So whatever I stick in the memory just stays there, doesn't change over time. That's a memory. And then these methods let you build a spiking neural network that will approximate those dynamics in neurons. So we talk about three principles. We talk about the principle of representation, which you can just think of like high-dimensional vector representations. Talk about computation, so taking those representations and being able to compute some nonlinear function of them. And then the principle of dynamics. How do you take high-level dynamics and embed them into kind of neurally constrained dynamics, right? So neurons and neural connections have particular dynamics that we measure and are very familiar with, and they're determined by things like neurotransmitters and so on. How do we keep those constraints in mind while implementing a dynamical system, performing some computation over some representation? So, what those principles let us do essentially is take any thing that you formulate in this way, and that's your high-level language, and then build a spiking network that implements those dynamics, like I said. So this can be very useful for building neural controllers or memories or decision-making systems. Like, I think pretty much everything the brain does can kind of be written this way. So ideally, this is a very general technique, and it lets us do this kind of compilation. And what this helps us do is represent or answer the question, how does the brain compute, right? So if somebody said, how does the brain compute? I'm like, and we call this a 0th order guess, just so you know, we don't think we've solved all the problems here, but I think it gets you in the right direction, how brains compute. Of course, that doesn't tell you what brains compute, right? So if you know the function that brains are computing, then this might be a way of generating a spiking network that you can compare to the real spiking network and see, did we get the mechanisms and the dynamics right potentially? So the second question is, what does the brain compute? And so the very first Spaun model was actually the 7th chapter of this book. So this book came out in 2013. So we published the paper in Science first, and then published a kind of book-length sort of discussion of what the architecture was, how it was built, and all these kinds of things. And there's a bunch of philosophy and stuff in there as well. But the point of this was to basically say, what is the architecture that we think is a reasonable one to capture what mammalian brains do, how they're organized, what the key components are, and so on. And so this let us build this big brain model. The version 2 has about 6 million neurons in it, which turns into about 20 billion connections. So at the time it came out, it was, I think, the largest, but definitely one of the largest neural networks, artificial neural networks anyone had built. And I think it remains the largest recurrent neural network, right? So most of the big ones that you hear about, they're feed-forward. This is definitely not feed-forward, right? It's very recurrent. In the model, we have 4 different types of neurotransmitters. We have anatomical and physiological mappings between the components of the brain and the components in the model. They're matched, so you have the right types of activities and things, and neurotransmitters in the right types of areas. And the most important thing for us is that it's functional, right? So there have been other large-scale brain models, but they typically don't sort of control a body or execute a task, right? They've often just been very big simulations. So in Spaun 2, that functionality basically we described in terms of 12 different tasks. There's a bunch of them. I'm not going to go through all of these in detail, but part of the point was to show that the model doesn't change between performing any of these tasks, right? You just tell it which task you want it to perform, and it goes and it does that task. And so you give it input, and it will process the input, and so it does things like counting. It does all kinds of stuff. So I'll give you a couple examples of those. So right, so here's the model. You can see it's seeing images. It's got one eye fixed. It's got a single arm. It's controlling its arm with these muscles. What it's doing at the beginning here is it's basically writing down a 1 if the 2 images are from the same category, and a 0 if they're from different categories. And now it's just drawing out whatever digit it sees. So we're showing it different images, and so it's kind of doing a classification plus a drawing task at the same time. It will, let us, because right, as you mentioned, because it's an artificial neural network, we have access to all the data, right? There's no missing data here. We can look at all the spike trains, every spike time, everything. And so, we can record everything that's going on in what V1 of our brain model is. And then you can also see the decoding of the V1, right? But you'll notice that in order to perform this writing task, that's not enough, right? You have to not only know what digit you saw, but you have to remember that over some length of time. So you can see in more frontal areas, you've got something like a working memory where it will stick around for some length of time. And then that information is given to a motor system, which is basically plotting a set of points in a 2D space, which is then projected into a 6-dimensional space to control the activities in these muscles, which generate torques on the joints and let it draw things out. So the nice thing about this is that you can do exactly this task in monkeys and humans and in the model. Same exact inputs, same outputs, same analyses. You can go and analyze these with whatever your favorite sort of spike time method is and all that kind of stuff, as well as look at the behavior, right? How long did things take to respond? What happens when you do different kinds of perturbations or damage to the networks in different ways and so on. So that's a nice sort of simple example. One thing I did want to show is just that the visual system, like it can't draw complicated things, but it actually can do essentially classification over about 1,000 different categories. And so this is kind of like the internal full model through the ventral stream of the model. And you can see interesting things, like you see increased sparsification over time and other sorts of things that you know are properties of what we think the way visual processing works. You see make mistakes, but you can see that it's doing some sort of fairly interesting visual task. It's actually executing a function, and it's doing this all in spikes. So we can take that data and we can do an analysis on it that looks like the same as the analysis we do on monkey data, right? So here's an example where we've shown a bunch of the same images to the model that were being shown to monkeys. We then took the same analysis method that they used in the paper, where you're basically doing some kind of analysis on the timing of spikes given the sorts of inputs that you're providing, and then see that we find very similar tuning in individual neurons. And the relevant thing here is that usually if people look into a vision model and they plot these, what they're plotting is weights, right? And that's actually a thing that you cannot measure very easily from animals. And so typically you're generating the plots in kind of different ways, and you could worry about whether that's telling you the same information. But in a case where we've got all of the spike timing, et cetera, then you know that the method for doing the data analysis is not going to be changing between the two instances. We can look at things that are kind of more dynamic. So this is a bandit task. So basically, rodents are walking up to a decision point and then deciding to go left or right, and there's reward with some probability on either side, and you can switch the reward probability. And so they learn over time. It's like a reinforcement learning task. Learn over time which way is going to give them the most reward. And here we have the model doing the same thing. In the case of the model, it's not walking through an environment. It's being shown digits, 1 or 0, with different probabilities, and then it has to pick which digit is basically, or it has to guess which digit is the most rewarded, and when it writes a digit out, it will get a reward, et cetera. Anyway, so what you can see though is that you've got very similar sorts of dynamics over the delay, approach, reward, and return segments of the experiment, which the original experimentalists had identified. And you can do, again, the same sort of analysis to find that you have a lot of the same kind of sort of dynamics of the neurons over time. And again, you can plot all the spikes, both from the rodent and from the model. And maybe there's an issue here with your model. Maybe something needs to be improved in order to fix that, although it's hard to tell because we don't have confidence intervals, unfortunately, from the original experimental data. But that gives you these are just like different types of analyses you can get out of this large scale model. But then, of course, the other thing, we wanted to make sure that it was really a cognitive model. So it was doing things that essentially humans do and most other animals don't. So this is an example of that. So this is patterned after the Raven's progressive matrices intelligence test. So you're supposed to figure out what goes up there at the end. And so you as a human probably have no problem doing this task. And so we can watch the model do the same thing. Now there's some key differences, like we have to present everything in one place because the model doesn't move its eye around. So it's being shown these triangles to basically indicate when a particular element in the matrix has been completed. But it's just like you, it's kind of never seen this before. So it has to figure out the pattern by seeing it the first time and figuring out what sort of explains the change over time. And then when we get at the end, it writes out the right answer, which is presumably the answer that you got. We can perform this task on like a bunch of Raven's progressive matrices and show that it gets about the same. It's a subset of the full Ravens, but show that it gets like the same accuracy on that subset as humans do. College educated students, I guess, is the direct actual comparison. But the idea being that this same model is now able to do motor control, decision making, perceptual, cognitive tasks, right, all inside the same model. And then the last thing I'm going to show is what we like to call mental gymnastics, because this is essentially taking a bunch of the skills that the model has and putting them together. So it's also called instruction following. So just to give you a sense of this, I'll get you to follow the following instructions and see what you come up with. And it's analogous to what we think the model is doing. So imagine the letter V, capital letter V. Imagine a capital B and rotate it 90 degrees counterclockwise. And then put it on top of the V and erase the back of the B. And what shape do you have? B, back of the B. Yeah. Yeah. What did you say? A 3? If you just, yeah. But so you have to take a V, you put the, so we got the answer here. Anybody else get the, yeah? Yeah, exactly. So yeah, you take the V you put a B on the back of it and erase the back, right? So you have this heart shape, right? Some people call it a 2-scoop ice cream cone shape too, which I guess I can see. But in any case, so what you were doing, right, is you were generating internal mental representations, you were manipulating them in particular ways, you were associating them with each other, and then generating a final answer. So the same kind of thing is going on here. So this is basically doing something like the Raven's matrix. So it's trying to find a pattern in some inputs that we're providing to it. It's then going to do a question answer task where we give it a bunch of input. So it's like a working memory task. We give it a list, and then we ask it a question about the list. But the question is going to be formulated in terms of the pattern that was found here. And then we're going to apply the pattern to the list. And in this case, apply means add. So basically, if we find some pattern like 4, and we have some list here, then we'd add 4 to whatever the list is. So every item in the list would be incremented by 4, and then you'd have to say the answer out. And then we're going to apply the pattern that we found to the position we were asked about, right? So kind of like asking to take intermediate mental representations and combine them in some interesting way. So it goes by pretty quick, which is why I explained it in advance, but you can play it more than once. So, right, so it's starting off and it's basically saying what's the relation that is between 1 and 3 and also between 2 and 4. So it's increment by 2. And here's a question, right? What's at position 2 in this list? So it writes out a 7. And then let's say apply the pattern to the list, so the 2, so it gets 6, 9, and 4. So it's adding 2 to every item. And then it's being asked to apply the pattern that it found here to the position. So it's adding the 2 and the 2 and getting 4. Right. Okay, so the idea here is basically it's following, like this is a set of instructions that's been loaded into its working memory, and then you're giving it a bunch of input, and it can follow these for whatever input you give it. That's valid, basically. And if it's invalid, it just kind of stops and waits until you give it valid input. So yeah, so it's an example of kind of doing the sorts of things, and we can't. This is one task, so because it's instruction following, you can kind of get it to do many tasks because it will follow instructions, but it's sort of an example of the most complicated task, I'd say, that Spaun 2 did. All right, so just to give you a sort of bit more information about the model, here's an anatomical view of the model. So you can see sort of standard brain areas, so posterior parietal cortex, motor areas, and one SMA. This is basal ganglia, so it's actually subcortical. Visual system, anterior infratemporal thalamus, also subcortical, et cetera, right? So you've got all of these different brain areas. All of the connections that are in the model are in the brain, unsurprisingly. The converse is obviously not true. But we've got the right kinds of connectivity going on here. So these are all mostly inhibitory connections inside the basal ganglia, as you find in real basal ganglia. You've got the properties. You've got like striatal D1 and D2, so different types of dopamine, et cetera. You can also take this functional perspective, right? So these colors, it's like this dotted orange line around action selection, right? So that's a function, is the same dotted orange line that was around the basal ganglia, right? So you can see some of the mappings between function and anatomy in here. But you can see that there's no label of a task name in here. This is just a bunch of different information processing combined in different ways to perform the tasks that it performs, right? So things like processing the visual input and encoding it, being able to store information over time, being able to take sort of output, decode it, and then turn it into some sort of motor command, being able to evaluate rewards and update representations based on rewards. And this is for transform calculations for like inferring how two inputs relate to one another. Like what is the transform that gets you from one to the other? So that's critical for doing the Raven's progressive matrices. So this is a perspective which I think is important, that we take the kind of key information processing components to be important, and they're not really task specific, right? It's more like what are the things that brains need to do that are then combined into doing all those tasks. And the combining part happens basically through the basal ganglia action selector, right? So it's monitoring this is all cortical, right? It's monitoring cortex and all the different kind of cortical states. And depending on those, it will affect these, what you can think of gates. So it will basically determine what information flows at some point in the task into working memory, right? Or into reward evaluation or into information decoding, right? So it's kind of controlling information flow in order to perform those tasks. And it itself is actually not a particularly large part of the model, but it's playing this fairly essential role. Okay, so that's the original or the second version of the Spaun model. What are the shortcomings of the model? There are many, many, many shortcomings. It's 80,000 times smaller than a human brain, right? So it's kind of tiny in some ways. One key one for us is that it has no environment and body, right? It's a disembodied eye staring at a screen and an arm. Clearly not a great sort of model for most biological systems. So really, this is kind of the key thing that we wanted to address with the next version of Spaun, right? We want to put it into a 3D world, give it a body, make it do tasks like navigation is the obvious thing that you can do in a 3D world, and related things like you can do, sort of scrounging around looking for different sorts of things, and you can do working memory in a 3D environment and all that kind of stuff. So that's really what we were interested in. Another sort of key limitation is that most of the high-level representations were discrete in the previous model. So, doing the Raven's progressive matrices, you've got digits, which are discrete. You've got some numbers of digits in each of those different boxes, which are discrete. And, it could kind of do language-like processing, but again, it's all very discrete. And as I was arguing at the beginning, things like maps, which of course, if you want to do navigation, you have to have, are much more continuous. And so even if you just look at the kind of working memory model, in the original Spaun, it's kind of a model where you've got these virtual slots, and you can put items into the slots. So you can put digits into each slot, and then you can decode any slot. So when we were doing the question answering, what was in slot number 2, it could answer that question, okay. But it's not really able to answer questions about like how far apart in time were these two, or any of those sorts of things. So all the representations are kind of discrete. So it's good for language-like representations, Raven's progressive matrices, and list memory, but bad for continuous maps. So in something like the list memory, you've got basically a fixed number of, or you don't have a fixed number of slots, but you've got discrete slots. Each slot is its own thing. In a map, you can think of a map as having continuous slots, right? Like every position in space, there could be a thing sitting there, right? At every metric position. And so you should be able to like put a jug, which is sitting in the corner of the room, at the corner of the room. Or you should be able to put the same jug kind of 1 meter away from the door, and et cetera. It could be floating up somewhere, right? You should be able to kind of have those features represented at any location in the space. Okay, so so these discrete representations aren't something you want to get rid of, right? I think they're key for language-like structures. And in representing them in the original model, we use something called vector symbolic algebras. And they have a couple of operations which basically let you do things like binding. So they let you kind of like define a slot and then bind a filler to the slot. And then you can have lots of slots and you can add them all together. You can do similarity operations to see which things are similar to which other things. You can unbind things from slots. And so interestingly, those same operators can actually be used to define continuous slots in maps as well. And so this is something that we've been working on recently, and we're introducing into Spaun 3 because we've got it working really well for doing things like navigation in and doing path integration and basically all the things that animals seem to do. And we can replicate things like place cells, grid cells, time cells, like all of these sorts of things that you again find in the hippocampus, which are important for continuous space and time representation. We can get using our vector symbolic algebras and related techniques. So yeah, so continuous space representations, we have some publications on that. We also have work on continuous time representations. This is actually turned into what people in the AI literature know as state space models, right? So these are kind of often touted as the next generation of transformer. They're much more efficient and so on. And so we published the first state space model back in 2018, 2019. And that's also the kind of thing that is really good at representing continuous time, because it's basically introducing dynamics into neural networks. And we can use those techniques for doing things like introducing language models potentially into a model like Spaun as well. Right, and these are from biology, right? So this is, as I was saying before, like one connection between AI and biology, in my mind, is basically state space models, right? That's where they came out of, looking at how time cells can be modeled in the brain. So on to Spaun 3. What are we doing in Spaun 3? So so far we have picked Isaac Sim. So this is a standard robotic simulator to be our physics engine and our visualizer. So you can see the body and see space and all that kind of stuff. We're using Nengo, which is an open source package that was first developed in the lab to do all of our spiking neural network simulation and non-spiking. The first thing we looked at doing was implementing SLAM. I guess I should also say, like, one of the things we want to do in Spaun 3 is all of the stuff that Spaun 2 did, plus more, right? Like, we don't want to kind of lose any of the skill set. And so, yeah, I'm not going to talk about that, but that is part of the goal. So instead, I'll focus on the new stuff. So in this case, it's doing simultaneous localization and mapping in a spiking network and be able to, put that into this Isaac Sim simulator. That means that we're going to have a better vision model. So it has to do things like estimate depth in 3D world and things that it didn't have to do before. We have to implement control in the body. So we have to be able to move around as well as control the arm. So, we have a good leg up on the arm control, but still have to do walking and so on. We also have built a navigation-based spatial working memory experiment. So we found a good working memory experiment that had been done on humans, which I'll talk about shortly, and replicated that in the simulator. And here it is, or here's our environment to start with. So this is a top-down view. This is the thing that we call the arcade, which you can see the little agent standing there. The arcade has a screen in it where the agent can stare at it and basically do all of the experiments that it did before. Maybe I won't talk about that. It was instructive. And so initially, we tried to take all of those experiments we did on the screen and translate them into 3D equivalents, but you cannot do that, right? Which gives us, I think, is very important to realize when you're doing those kinds of experiments, that's what you're learning about, right? You're not necessarily learning what it would mean to then put that in the real world and have people, with a body moving around in space, et cetera. Then we also have this part of the environment, which is where it can move around in 3D space, and we're basically replicating a working memory experiment that people have done in virtual reality, because you need to do that in order to get brain data at the same time, or detailed brain data. All right, so yes, so this is as I mentioned, the arcade. So this kind of looks exactly the same as before, and now it's going to reproduce all of the tasks that I've already talked about. This is the working memory experiment. So the way this works is you put people in virtual reality. These are all people who had MEG, so right on cortex, basically doing hippocampal recordings, so we can get like detailed neural data from humans. And essentially what they were doing is they were in this environment. They would walk up to a chest. The chest would open when they got close enough, and it showed them an item. So this has an hourglass in it. And then they would be directed to go to the next one, and they would look in that box, and then this has a bunch of wooden logs in it. Then they would do a distractor task where they have to kind of just, do the shell game. You've got something kind of hiding from you. And then they're queried about what they remember. So they're asked, do you remember where the wooden logs are? And you either say yes, maybe, or no. And then you're asked to indicate where they are, and then you're given feedback about, did you get it right, or were you wrong, and where was it actually, right? So it's kind of a standard working memory task. You can see here over a bunch of, they had 43, I think, or 46 different patients, and they got accuracy across the task. They also looked at accuracy as a function of the confidence reported, and the accuracy as a function of the, you can basically, these colors are matching on, and you can see how the confidence and accuracy are related to one another again. And then also important for our purposes is we have hippocampal data, right? So they distinguish between left and right hippocampus, and they look at times when it was a recalled object or not, or there was no item. Sometimes these are empty, right? And so they also have a no item condition. And so that is what we take ourselves to be trying to replicate. We haven't replicated the details of the hippocampal data yet. We've got some intriguing first passes, but I'm not going to show you that. I'm going to mostly just focus on behavior for now. So here, this is a top-down view. This is the internal representation of the agent, right? So this is going to be like, what does the agent remember as it walks around through? And you can see we've got all these boxes set up, and it's going to walk past the different boxes and see different things. So this is its first-person view. This is where it's walking, and you can see we've got the actual desired and inferred paths, inferred being where it thinks it went. And so here it's coming up to the objects. These are a little bit out of time. And then the box is disappearing, and then it's generating a representation of the object being at that spatial location. And you can see over time that these drift a little bit, but by the time it gets to the end, it's kind of seen all of them. It's got some representation of where they all were in space. And then we can go and query the agent and say, like, where did you remember? Where was the banana? Right? We can also look at the activity in the hippocampus of the model, part of the model. And so here in entorhinal cortex, this is basically doing all of the where am I right now, right? So this is all grid cells, basically activity. And CA2 is when it's encountering a new thing in the environment. You can watch how the activity changes when it's basically saying, oh, there's an item there I'm going to have to remember for later. So it's actually quite dim, unfortunately. But there's a bunch of activity going on here, which is kind of slowly moving around. And here you don't see a lot of activity until it actually bumps up into one of those objects. And then you'll see a kind of little burst of activity in here. I hope, yeah, there you go. That was very brief. You can see more subtlety in the version on my laptop, but you get the idea, right? So this is the data that we can now take and do sort of filtering to compare to the neural data that they recorded from the agents or from the patients. Right. So one thing that we want to make sure is that we have the low-level single cell data correct. And so this is showing examples of different types of cells that are in the model. Right. In the gray in the background is a sort of movement of an agent throughout an environment. And we've done comparisons. We've taken like the same movement that you have on rodents and demonstrated that you get these effects there as well. So you can see things like grid cells, right? And you can see over more time, the grid cells become better defined. You have things like object vector cells. So these X's are where objects were. And you can see cells that are sort of firing whenever the agent is within some consistent egocentric relation to the object. And you can also find place cells where whenever the agent goes through that place, there is activity of a cell and so on. And then we can also compare the behavioral level accuracy. So here what we're doing is basically matching the human and model recall accuracy. So this is the graph that I showed before. And here's the accuracy in the model. And the one thing that we're changing basically is how many grid points are used by the agent to decode its estimate of spatial location. So you can see if you use a lot of points, so 50, you actually get extremely good superhuman performance. It's like the model is essentially never wrong. And so in order to match the human data, we basically had to decrease the sampling of the space in order to estimate where the object that it had encountered actually was. And in so doing, you can find one particular, or there's a range of values, but some values which give you a pretty good match to the accuracy, behavioral accuracy that you find in humans. So this, for the time being, is something of a hypothesis about why do people, and I will say people do kind of badly at this task, right? So they do worse than I would have expected. And this is one hypothesis for what's going on, right? Is that you basically have a non-great representation in order to try to do the decoding and to get your estimate of where the thing you met was in space. But I think this is an early hypothesis, and I think others will come along as we make the model more sophisticated. Okay, so that's kind of an example of one of the things that we've done with Spaun 3. And that's really trying to address like a new kind of neuroscience data that we couldn't get in earlier versions of the model. This is more of a connection to methods in AI. So taking the representations that we've got, so these vector symbolic algebras that we've got in Spaun, and using them to improve the performance on a large language model task. So what we would, one of the things we would like to do is add into the model, so we're still building it, add in a large language model, a state-space model-based one. But then we also would like the reasoning in that model to be more human-like in the sense of being able to accurately do things like simple math problems. So Spaun can do step-by-step action execution, right? So you can essentially give it in the basal ganglia, you can give it a kind of algorithm and it can go through the steps in the algorithm, right? We saw that in the mental gymnastics task. So we know we have that kind of ability, something which you often are lacking in LLMs. And so what we're going to do is rely on that and use the same representations we're using in Spaun for doing structured representation, this vector symbolic algebras, but try to introduce those into an LLM and show that if you have that and a stepping algorithm, you can get improved performance, right? So that's kind of the job we have for us. And I think this is going to be an example of demonstrating that merging bio-inspired models with AI methods can actually get you something that you don't get alone. All right, so here's what we did. So we tested this on math problems in particular. So a math problem would be something like, what is 910 mod 213? And we need a representation of the problem, right? So here's a vector symbolic algebra representation of the problem, where this operator is a binding operator. So it's basically saying, my hundreds digit is a 9, my tens digit is a 1, my ones digit is a 0, and that's for the first number. So the first number right, is bound to that representation. Second number is bound to similar representation for the second number. And the type of problem that we're doing, so the operator is modulo, right? So this is the kind of representation that once we have it, we know Spaun can go through the steps, right? And say, oh, if it's a modulo problem, then go through these steps, take this thing and do these manipulations and so on. So what we did in the case of the large language model is we took the large language model and stuck in just the sentence, right? Of course, you've turned it into vector or embeddings and all these kinds of things. So you've got the sentence going in. And then somewhere through the language model, we basically took the representation the language model had generated. We then encoded it, so basically taught it how to turn its representation here into this representation. Then executed the algorithm that we know will solve the problem, generate a representation that we could then stick back into the language model, right, and sum it into its representation and let it continue on its way until it generated an answer. Okay, so what we're essentially doing is we're kind of going in and saying, once you know that this is an algorithmic type problem, math problem to solve, you just represent the input in the right way, you execute the algorithm on it, and then it gives you the right answer, right? So this symbolic algorithm is the type of thing we'd like to be executable in Spaun. In the original paper, we're just doing it in Python, just to keep things simple and more friendly to machine learning audience. And when you do that, you find a huge increase in performance, right? So what we're showing here is like over all of these different math tasks, the blue line is the performance of the neurosymbolic language model. And then we have a couple of other comparisons. So we have the standard LLM in orange. We have a LoRa, so this is a fine-tuned version of a large language model in red. So you can see it does better on some things, but it also gets worse on other things. And then we have a chain of thought method. So these are like the standard methods people try to use to get a language model to actually reason better. So then we have chain of thought. And again, you can see it gets better at some stuff, but also worse at others. Another key thing here, these two tasks, addition and integer division, are things that the language model already does pretty well. And so we don't intercept, or we don't sort of encode it in this way and try to get to it because it already does fine. So we just let it do those problems the way it already does. And this is showing that when we do that, we also don't hurt the performance of the model, right, for tasks that it already knows how to do. So overall, this is a 73% higher absolute accuracy. So it's not a 73%. It went from like 5% to 90% on bitwise XOR and so on. So huge improvements. And so to me, this is the kind of thing there where what we did was basically take this bio-inspired type of representation, introduce it into a language model, and get a massive improvement in reasoning on particular task types. And now we're looking at generalizing it to more challenging things than math and so on. Yeah. So as I mentioned, it's a work in progress. So we also have a couple of other sorts of next steps that we're looking at. So we're improving the working and long-term memory to do things like capturing temporal distances between objects and lists and so on. We also need to tell it in the original Spaun model, we would show it the digits, like say, A1, and then it would know which task to do, or A5. It's not in front of a screen all the time anymore. So in order to tell it what to do, we're going to give it an auditory system. So we just tell it what to do with words, which is, I don't know. These are hard decisions to make about what to add into your model and what not to. But it seems like a pretty reasonable thing to do. Animals are fairly good at responding to verbal commands and so on. So having an auditory system that then lets you interpret the input as a command seems like a fairly reasonable thing to do. We are adding a path planner. So right now, when it was doing the memory task, actually the humans doing that memory task, they're told where to go. They don't have to plan a path, so it's kind of okay. But ultimately, we want it to do things like foraging tasks as well. And so it needs to be able to plan paths. So we're working on that. Maybe adding a second camera for improved depth estimation. It does okay with what it has. So that is maybe a complexity we don't need. We could do things, we have amygdala models, which would introduce sort of more emotional processing. So getting like fear conditioning and so on in there. So these are questions in our minds, right? So I'm always happy to hear people's opinions about what would be the most compelling things to add into a model like this. And yeah, I just wanted to kind of mention this as us seeing the relationship between AI and neural modeling, large-scale neural modeling like we're doing, as being a two-way street, right? So we learn things from AI for sure, right? It's like the surprising impact of just scaling these really data-driven methods, right? The kinds of things that LLMs have learned to do is really quite impressive. being able to have useful starting functional systems and be able to kind of turn them into something which is bioplausible. So right now, I think our best models of the visual system are basically deep learned models, right? So we definitely have exploited that kind of thing in neuroscience. And then the other way around, right, is that you often have surprising efficacy of bio-inspired either architectural or representational constraints, right? So state space models are one example of that. So introducing sort of like dynamics that were not previously in these models can be very useful. Putting in architectural constraints, like just the way that you set up your cognitive model in order to like figure out when to use different components in order to perform a specific task, or in the case of representation, introducing these VSA representations into the LLM in order to get it to perform better. And then these are kind of those examples that I just mentioned. And yes, thank you for your attention, and I'm happy to take any questions.